Welcome guys, and in this video we are going to talk about the equal roots case. So eigenvalue and eigenvector method itself, eigenvalue and eigenvector method, but for the equal root case. Okay, so in the first case what we have seen is, let's say if you have so let me recall the whole thing, yeah, that will be much better. So let us assume that we have this problem, x prime t equals to a of xt, clear, and we have seen that one admits a solution, okay. Do you think it has a unique solution? Of course not. It will have infinitely many solutions because of the linearity and homogeneity. Here, so one admits a solution x of t which looks like e power lambda t. Okay, so this is a real, lambda is real, t is real, times some vector v, if and only if lambda and v is an eigenpair. Here is an eigenpair. Okay, and we have seen that we already know. So let's say A is given to be a n cross n matrix, right? So we already know the solution space of this one is a n dimensional solution space. The dimension of the solution space is n, right? If A is given to be n cross n. So in that case you need to have x1, x2, xn linearly independent. So basically for solution space of one, we need to find n linearly independent solutions. So basically you see you need x1 of t, x2 of t, okay, and xn of t. See, this is v here, that is a vector, that's a column map vector. Okay, so v will look like this, no? v1 vn, clear. So essentially x1, x2, xn will look like this. We need to find x1, x2, xn such that they are linearly independent. They solve one and are linearly independent. Right? And then you can span, one can span x1, x2, xn to get the whole solution space. Okay, now how do I get those linearly independent solutions? So what was the case 1? The case 1 is if you get v1, v2, vn are linearly independent. Okay, eigenvectors, okay, corresponding to some eigenvalues. So you see, it can have repeated eigenvalues, it can have distinct eigenvalues. So let's say you have n linearly independent eigenvectors. Okay, then of course you have n linearly independent solutions, right? Solutions of one which span the whole solution space, I think it is clear now what I am trying to say here. First thing what I am trying to say is, let us assume that you have some. So essentially what I am trying to say is this. So let us assume that you have some vectors lambda 1 eigenvalues lambda n. Okay, they may be repeated or they may be distinct, for which you have corresponding eigenvectors which is v1, v2, vn, which are linearly independent. Okay, so this can have repetition, but they can be distinct also. But v1, v2, vn's which you are going to get are linearly independent. In that case you can just write x1, x2, xn to be e power lambda 1 of t v1, e power lambda 2 of t v2, like that, and you can actually show that they are linearly independent and spans the whole solution space. You are done, right? Case 2, we have seen that if v is alpha plus I beta complex, okay, not v, lambda, okay, if lambda is alpha plus I beta and v is v1 plus I v2, okay, then how do you find linear independent, how do you find solution? So it depends on the the size of a, but the thing is exactly the same thing. Then you can say that if alpha plus I beta and V1 plus I V2 is a solution, then you can break it up, and the real part of e power alpha plus I beta, okay, and V1 plus I V2, this thing, and imaginary part of again e power alpha plus I beta and V1 plus I V2. Okay, so they are real solutions, okay, real solutions. One sec, sorry, real solutions. And of course you can get linearly independent solutions like that, and once you get it, you can just write it down and to span the whole space. So this is also easy case. So these two are easy cases. Okay, now let's come to the difficult case, which is the equal root case. Okay, equal root case. So in this case, what happens is this: essentially, you see, we know that xt equals to, so this is from our earlier kind of idea. Let's say e power xt, if you just small xt, given by e power at times c, c is some scalar. So this solves this problem, right? X prime equals to ax, right? Okay, and therefore xt, capital Xt, which is given by e power at times v, solves, you can say that this solves this problem x prime equals to ax for some v, right, which is the n cross 1 matrix. Do you understand what I am trying to say? See, since x of t, small x of t, this is a real valued function, real variable, okay, xt equals to e power at times c, solves x prime equals to x, okay, think about it. Then you can say that xt, which is given by c, this a I am changing it to capital A times v, and some vector, arbitrary vector v, that solves x prime equals to x. This we already know this stuff, right? Okay, so v is an arbitrary vector here because there is no initial data given to us, okay. Yes, and we know now how to define e power at and everything. But now what happens here is this: see, you can actually write e power at times v like this. Now, so we know that there is a solution of e power at times v which solves x prime equals to x, right? That we know, we did this earlier. So now you see e power at times v. Okay, what we can do is this: from here we can write it like this: e power lambda I, okay, times t, e power lambda I t times v. I hope this is fine. Here we see, this is a equal root case, this is a complicated case, so we are looking at it from a different point of view. Okay, we are writing e power at times v to be this. Now you see a minus lambda I and lambda I, these two vectors, they are commutative. So basically what I'm trying to say is, since a minus lambda I, okay, and lambda I, this vector is equals to lambda I times a minus lambda I, okay, this vector, so they are commutative. Hence e power lambda it, okay, what is e power lambda it? So basically we want to write it properly, you understand? Okay, so let's see what is e power lambda it. If you just write it, it is becoming I plus lambda it plus lambda square, the identity square, t square by 2 factorial plus goes on to infinity times v. Now this I can write it as 1 plus lambda t plus lambda square t square by 2 factorial plus it goes on like this times v. Okay, now do you think that I am changing I to 1? Just take 2 seconds, just think about it. No, right? We are not doing that. See, what is happening here is this: let's say let's do it at a 2 cross 2 case. Okay, I this times v, so I is 1 0 0 1, let's say, and this is v1 v2. If you multiply, it is going to be v1 and v2, right? So that is basically 1 times the vector v, right? So that is what I am writing, 1 times the vector v, and similarly the other parts also the same exact same thing. Okay, that is why I am not changed. I am not writing a matrix as a scalar, but the thing is this matrix multiplied by v is basically 1 times v. So that is what I am just writing. I am just rewriting this thing, that's all. Okay, now if we have something like this, then what does that mean? It means that it is equals to e power lambda t times v. Okay, I hope this is fine, because this is your series for e power lambda t. So this is e power lambda t times v. Therefore, you see this particular thing, e power at times v. Okay, how does it look like? It looks like e power lambda t, okay, times e power a minus lambda I t times v. Clear? Since this is commutative, I can write this thing on this side and this thing on the other side, right? Okay, ab equals to ba in that case. Okay, since this is commutative, you know this is the property of an exponential. Okay, since this is happening, we can write it like this, and once we write it like this, this v is essentially I can just keep it out, okay, of the whole thing, and so basically e power lambda I t can be written as e power lambda t. Clear? Okay. So yeah, so now what we are going to do is we are going to make a very important observation. Okay, see, let's say that if v is such that, see here v is an arbitrary function. Okay, I don't know what v is, some v, for some v. Okay, I don't know what v is. I need to find what v is. So let's say that the choice of v is on us, right? So if v satisfies a minus lambda I times mv equals to 0, okay, for some integer m. You understand what I am saying? For some integer m, if it satisfies this, then look at e power at times v. What happens here? It becomes e power lambda t e power a minus lambda I t times v. So you see this series, if you just break it up, what does it happen? What does it means? E power lambda t, this series is v plus t a minus lambda I, okay, times v, plus it goes on like this, t power m minus 1 by m minus 1 factorial a minus lambda I power m minus 1 times v. Clear? If you just break it up, it will look like this, no? Because m is 0. Yes, m is 0. So what does that mean? It means that you see, since a minus I lambda I times m, the mth power, so basically it is a nilpotent matrix, so of order m, right? Okay, you can think of it like this. Okay, so basically a minus lambda I whole power m times v, that is going to be 0. Okay, that means that a minus lambda I whole power m plus k, yes, v, this can be written as a minus lambda I whole power m a minus lambda I whole power k, okay, times v. I can write it like this. Okay, now you see, so essentially what is happening is, yes, yeah, so essentially what is happening is this, let's write this thing as k, let's write this thing as m. Okay, k and m. Okay, now so essentially, so basically I have that this yes, yeah, you see a plus minus lambda I whole power m plus k times v, that can be written as a minus lambda I whole power k, a minus lambda I whole power m times v. Now a minus lambda I whole power v, that is going to be 0, because that is given to us. We are assuming that this is the case. So hence this becomes 0. right? This becomes 0. Okay, so because a minus lambda I whole power k acting at 0, that is going to be 0, clear? So therefore what is happening is this e power lambda at will look like this. Okay, so this will actually give you an algorithm of how to find n linearly independent solutions. Okay, so let me put it properly. So the case 1 is this. So how to find n linearly independent solutions of 1. Okay, solutions of 1. Okay, now first step is this: find all eigenvalues and eigenvectors, so basically eigenpairs. Okay, eigenvalues and eigenvectors of A. Clear? Now if A has n linearly independent eigenvectors, okay, if A has n linearly independent eigenvectors, then of course you have n linearly independent solutions given by e power lambda t times v, right? I mean for v1, v2, v. What is happening here? See, if there are eigenvalues and eigenvectors, so let's say lambda and v is an eigenpair. Okay, for such a v, what is happening in this series? In this series, you see this term is going to be 0. For such a v, a minus lambda I, since lambda is an eigenvalue, for such a lambda and such a v, a minus lambda I, v is going to be 0. So this term is gone. So essentially you are left out with v e power lambda t. So see, it is v e power lambda t. Okay, in that case it is the case. Now let's say, suppose that A has only k, okay, which is less than n linearly independent eigenvectors. I hope this is fine. Eigenvectors, okay. Then you have only this. So basically xi of t will be given by e of lambda I of t times vi. Okay, for I equals to 1 to k are linearly independent solutions, okay, of 1. Okay, now my problem is this: how do I find more solutions? See, I have from here I need to find n linearly independent solutions. I have k. So how do the question boils down to this: how to find the additional n minus k linearly independent solutions, right? That's the question. Now how do you find it? So let's do that. Okay, now how do you find it? So basically to find the additional solutions, okay, to find the additional solutions, okay, we pick an eigenvalue, any eigenvalue. You pick any eigenvalue out of these three. Yeah, I mean, of course, if it is a n cross n matrix, you have actually, I mean, you have n eigenvalues, right? It can be distinct, it may not be. I don't care, but as long as they are n number of eigenvalues. So we pick an eigenvalue, whatever it is, yeah, eigenvalue. Pick any eigenvalue, okay, such that a minus lambda I square times v, this is going to be 0, but a minus lambda I times v is not 0. Is this, do you understand what I'm trying to say? See, here what I'm trying to do is I need to find the additional n minus k linearly independent solutions. To do that, what I'm going to do is I'm going to pick any eigenvalue. You pick any eigenvalue, let's say lambda. Okay, and we want to find a v. Okay, so the question boils down to this. We want to find a v such that a minus lambda I squared times, so lambda is given to you, a is given to you, I is given to you. You need to find a v such that a minus lambda I square times v is 0, but a minus lambda I times v is not 0. So basically it is not an eigenvector. V is not an eigenvector. You understand what I am saying? Of course v is non-zero, we are choosing it like this, yeah? V is not an eigenvector, but something generalized. Okay, so we call this sort of V as a generalized eigenvector. Okay, so basically V does not satisfy a minus lambda I v is 0, but this is non-zero, but a minus lambda I square times v is 0. Clear? Okay, and for such a vector, what happens is, you see, e power at times v can be written as e power lambda t, e power a minus lambda I times t v, right? And if you write it down, what will happen? E power lambda t v plus a minus lambda I of tv, right? That's what you are going to get. Okay, so this is an solution of one. Okay, understand? Now also do it for all other eigenvalues. I hope this is very clear to you, the algorithm. First thing is this. See, we have k linearly independent eigenvectors. Yes, I need to find more so that I get the n minus k linearly independent more additional n minus k linearly independent solutions. How do I get it? In that case, I am trying to find a v such that a minus lambda I square v is 0, but a minus lambda I times v is not 0. Okay, if that is the case, let's say you can find a v. We don't know if there is. Let's just assume that there is a v like that. Then for such a v, e power at times v can be written like e power at times v plus t times a minus lambda I times v, right? That is also going to be a solution. Okay, so now you do it for all eigenvalues. So this is for a fixed eigenvalue lambda. You have n eigenvalues like this. Okay, not n, but you have some eigenvalue like this. Do it for all those eigenvalues and find out all possible solutions like this. Now, if you have all, n linearly independent solutions, you can just take the linear combination, find general solution, you are done. If you still do not have enough, so the case 3, if we still don't have enough solutions, linearly independent solutions, okay, then we find v such that a minus lambda I cube v is going to be 0, but a minus lambda I times iv is non-zero for I equals to 1 and 2. Clear? So basically what I am trying to do now is this. See, if the second power is not doing the trick, let's just go to the third power. Okay, so choose any v, choose any eigenvalue lambda like earlier, and you try to find a v such that a minus lambda I cube v, that is going to be 0, but a minus lambda I square v is not 0. Clear? If that is happening, then e power at times v, what is it? It is e power lambda t v plus t a minus lambda I, okay, a minus lambda I times v plus t square by 2 factorial a minus lambda I square times v. So this is an additional solution of 1. Clear? So you do realize that now I have another solution. Now one question is this: do you really think that these are linearly independent solutions? You guys can actually check that they are going to be linearly independent. Okay, this is, I am leaving this part to you guys. Please check that they are linearly independent to the original solutions which you have already obtained. Okay, so like this. So essentially you got some other solutions. Now if that is also not enough, you go to the fourth power, you go to the fifth power, you do it like this. You do understand what I am trying to say? Okay, until unless you find out the whole set of solutions. Okay, now what is the guarantee that you can find all possible solutions doing like this? So is there a termination of this method? So to do that, we have a small lemma from linear algebra. This we are not proving. Okay, so this will actually guarantee, this lemma will actually guarantee that the process actually gives you all possible solutions. Okay, so you see, so let's say that p lambda, the characteristic polynomial of A, okay, is given by lambda minus lambda 1 whole power n1 and lambda minus lambda n whole power lambda k, let's say, whole power nk. Okay, so basically you have be the characteristic polynomial of A. Okay, so essentially what am I doing? I am starting out with A. I am looking at the characteristic polynomial of A. Okay, I have lambda k eigenvalues, lambda 1, lambda 2, lambda k with multiplicity n1, n2, nk. Clear? Okay, now suppose A has only Vj which is less than Nj. Okay, linearly independent eigenvectors, okay, corresponding to lambda k. Okay, so basically lambda k multiplicity lambda j. So see, lambda j, the multiplicity of lambda j is nj, right? But you are going to get, let's say, Vj which is less than Nj time linearly independent eigenvectors. Do you understand? Corresponding to lambda j, you are going to get Vj linearly. Vj is the number of linearly independent eigenvectors which you are going to get. Okay, then the equation A minus lambda j I square v equals to 0, okay, has at least Vj plus 1 linearly independent solutions. Is this clear what I am trying to say? See, for a part, so you pick any eigenvalue, let's say one of them, lambda j, and so corresponding to lambda j, what is the multiplicity of lambda j? Nj. But let's say you are only getting linearly independent eigenvectors, Vj linearly independent eigenvectors. Okay, so basically, so think about this. Let's say lambda j is some eigenvalue corresponding to which the multiplicity of which is, let's say, 5. Okay, for a huge, some 10 cross 10 matrix, let's say. So the multiplicity of lambda j is 5. Now let's say you have an corresponding eigenvector, the linearly independent eigenvectors which you are going to get, the number of them, let's say 3 linearly independent eigenvectors you are going to get. Okay, then if you look at the equation A minus lambda j I square v, okay, then that equation will have at least 3 plus 1, 4 linearly independent solutions. Okay, okay, 4 linearly independent solutions. Okay, solutions means linearly, yes, independent solutions. Okay, so basically, more generally, so you understand what I am trying to say. If it is square, just 1 extra. So if if the equation a minus lambda j I times m, okay, v has only mj which is less than nj linearly independent solutions, okay, then the equation a minus lambda j I power m plus 1 times v, this is equals to 0, has at least, you understand, one more, right, mj plus 1 linearly independent solutions. Okay, so I hope this is clear. Now, of course, if this is the case, then you can understand that there is always integer, some dj which is less than or equal nj, for which a minus lambda j I times dj is going to be 0, okay, with nj linearly independent solutions, and you can go on increasing. So basically, after some times, what is happening is the sum is going to be equals to n. Okay, that's the guarantee here. So please, if you do not understand what's going on in the lemma, please take up one or two examples, do that example, you see what is going on, okay, or think about what is going on, and try to figure out why if you take n1 n2 nk, that is going to be n, okay, so that is going to be the going to give, basically what I'm trying to say is this process will give you a linearly independent solution. That's what, try to figure out that if it is clear to you or not, okay. So let us look at one example. So this method in some books is also known as the method of generalized eigenvectors, okay. So let's look at one example. So let us say that you have a matrix given by 1 1 0 0 1 0 0 0 2. Clear? Now clearly lambda equals to 1 is a eigenvalue corresponding to the the eigenvector corresponding to this is given by 1 0 0. Okay. So this is a very straightforward case. There is nothing to do here. Okay. So you can just look at it. But you see, what are the eigenvalues here? Eigenvalues, if you just look at it, it is 1, 1 and 2. Clear? Those are the eigenvalues. Corresponding to 2, what do you have? So also lambda equals to 2 if you take. Okay, what is happening is this, you can of course choose a v which is given by 0 0 1. Okay, so you have 2. For lambda equals to 1 you have 1, and lambda equals to 2 you have another eigenvector, and of course they are linearly independent. Now this is a 3 cross 3 matrix, so you need to find 3 linearly independent eigenvectors. How do you find it? So you see 1 has double root, right? So basically let's start with 1. Okay, so we look for, now I hope this is clear, very easy, it's not very difficult. So we look for all solutions of the equation, a minus lambda I square v is going to be 0. Why I am choosing lambda equals to 1 here? So lambda is 1 here, so basically I will choose it to be I. Why I am choosing? See, there is no, for lambda equals to 2 has a multiplicity 1. I got one eigenvector out of it. Okay, so there is, I do not have any other option of getting any other eigenvectors out of this thing. That's done. Lambda equals to 2 is done. I want to, now my only other way, because lambda equals to 1 is a double root, okay, so repeated root, hence lambda equals to 1 is a natural choice for us. Okay, so a minus lambda is square v equals to 0. Now let's check what happens. If this is the case, then it becomes A minus lambda is 0 1 0 0 0 0 and 0 0 1 and 0 1 0 0 0 0 0 0 1, okay, times v. This is, if you calculate it, it is going to be, so if you multiply these two vectors, it is going to be 0 0 0 0 0 0 and 0 0, the last 1 times 1 is 1, okay, times v. This is going to be 0 0 and 0, right? Now that will actually give you what is the vector which you are going to get. V3 is going to be 0, right? From here you are going to get V3 is 0, so that will imply, so V, let's say, is V1 V2 V3, so therefore V1 V2 V3, V3 is definitely going to be 0, okay, and V1 V2 are free variables, so you can choose anything you want. You see, V is, let's say this is V1, and this is okay, let's say this is V1, superscript. Let me put it this way. Okay, so this is the vector corresponding to this is V2, and I need to find a V3 here, V3, not V3. Okay, I need to find what V3. The V3 is a column vector. This is just a component, the third component. Okay, so this is our V3. This is our V3. Okay, so V3 is, let's say, let me write it, V3 1, V3 2, V3 3. Clear? So 3 3 3. Okay, now you see the first vector is given by 1 0 0, the second is 0 1 0 0 0 1. So the third vector, since these are free variables, I can choose it to be 0 1 0. Okay, if I do that, then they are linearly independent, right? And hence, what are the solutions? The general solution is given by x of t is, first of all, this is corresponding to e power t times 1 0 0, e power t times 1 0 0, c1 times, plus c2 e power 2t times 0 0 1, plus c3 e power what is it? I am not yeah, this is fine, right? V1 V2 V3, yeah. Okay, one small thing, yeah, I missed this part. So essentially this is fine, but you need to check another part also. Sorry, I did not do that, so you should do that. Okay, but I need to check this also. So see, this is a V3 such that a minus lambda square V is 0, but I also need to check that this V3, so basically V3, this V3 should be, it's not cube, this is just a subscript. So this V3 must also satisfy a minus lambda times V3. This is non-zero. That also has to be satisfied. Okay, so I mean it's not a very difficult thing to see that that's non-zero. So you take 0 1 0 0 0 1 0 0 0 0 0 0 0 1 times this 0 1 0. That's not going to be it's not the zero vector. Clear? So that is fine. So hence, what is the solution? x2 of t. Please be extra cautious here. The solution is given by x2 of t. If you remember, see, the square is 0, right? But the first order, the first power is not 0. In that case, the solution is given e power lambda t. Lambda is 1 here, so e power t v plus a minus I tv. Okay, so it is going to be e power t e power a minus I times t, okay, times the vector 0 1 0. Clear? So please check this part. Here you do understand. There is nothing to check, right? This 0 1 0 0 0 1 0 0 0 0 0 0 1 times 1 0 0 1 0. That is not going to be a zero vector, right? That is quite clear because of the first component you see, that's a 1. Okay, so it's never going to be zero vector. So this V3 is a valid choice of V3. Now with that valid choice, what is x2 of t? It is not e power t that only this part, but e power t e power a minus I times t. See, this particular thing, e power t, v square is 0, this v is not 0, so the solution is given by e power t v plus a minus lambda I times tv. That is what I just wrote up. Okay, v is given by this, so that's the solution. Now if you write it down, I mean now there is nothing special about it. Okay, you can just write it down. Here calculating this is very easy. Why it is very easy? Because we already know that I mean a minus lambda square times 0 1 0 is going to be 0, right? So you can just write it out. It is e power t, it is 0 1 0 plus t times 0 1 0 0 0 0 0 0 1, the matrix A minus identity times 0 1 0. Okay, now if you put it together, it becomes e power t. Okay, let me just write it down. It's t 1 0. Now please check this part. So this is one solution, and the other solutions are given by e power lambda t 1 0 0, e power 2 t 0 0 1, and this is e power t t 1 0, and hence the general solution. Let me write it down, and then we are going to finish this thing. So the general solution is xt is c1 e power t, this is e power t 1 0 0 plus c2 e power 2t 0 0 1 plus c3 e power t d 1 0. Clear? So that's your solution, general solution. Okay, now if you are given an initial condition, you can just put it there and find out what c1 c2 c3 is, and you will be done. So I hope this is clear. Now see here, I mean our luck is good that this actually gave you the solution. Otherwise you have to go through cube and fourth power and all that, but in this case it won't be that much. Don't worry about it. Okay, so this is a small matrix, right? So I mean 1 or 2 steps is enough to do, I mean solve this part. Okay, so this is fine. Now with this we are going to end this video. I think this is clear.